Right. Welcome everybody to the third talk for Hilary term at the Oxford University Space and Astronomy Society. I'm your president, Hannah, and I'm very, very delighted and very humbled to have our fantastic speaker today, Jocelyn Bell Burnell. So to introduce our speaker, Jocelyn Bell Burnell is an astrophysicist who discovered the first radio pulsars in 1967. She obtained her BSc in physics from the University of Glasgow and her PhD from Cambridge. She has been awarded a number of highly prestigious prizes over the years, most recently the Special Breakthrough Prize in Fundamental Physics in 2018. She is a Legacy Fellow of the American Astronomical Society in 2020, and the Royal Astronomical Society's highest honour was awarded to her, the Gold Medal, this year, 2021. The prize money from the Breakthrough Prize has been used in full to set up the Bell Burnell Graduate Scholarship Fund, which aims to assist talented female, minority and refugee students in pursuing a career in physics research. And Jocelyn Bell Burnell has also served as president of the Royal Astronomical Society and the Institute of Physics. Jocelyn, was so delighted, so humbled to have your time and to have you here today speaking to us about your research. So without further delay, over to you.
Thank you, Hannah. Right, let's see if we can get share screen and everything to work okay. Can you see a PowerPoint slide?
Yes, we can see it.
Good. Right, let me bring up the text as well, just in case anyone finds that helpful. And a laser pointer. Excellent.
Great.
Well, thank you very much for the opportunity to be with you this evening. Thank you all for tuning in. What I want to do this evening is talk about a recently opened field of astrophysics, and one that's very rapidly developing, to give you a sense of what kinds of things are turning up. It's sometimes called time domain astronomy, but it's turning up a lot of transient events, and it's basically the transient events that I'm going to talk about today. You may be familiar with this image. It's known as the Hubble Deep Field. Hubble telescope stared at this tiny patch of sky for about 143 hours. It is a tiny patch. If you had a tennis ball 100 meters away, the area obscured by the tennis ball is comparable with this area. And it's well-studied field. Interesting things about it, there are relatively few stars. That one is a star because you can see the diffraction spikes. And I think there's one other very faint star somewhere that I can't immediately find. Again, you would identify it by the diffraction spikes. Everything else is a galaxy. And interestingly, there is still black space between the galaxies, even with this sensitivity. You're seeing up to 12 billion light years away, so it's a long way back towards the origin of the universe. But one of the snags about a long exposure like that is if anything moves, you get an extended image. So if one of these objects move, you get a cigar-shaped image. Equally, if anything changes brightness, either gets brighter or dimmer, that gets averaged out over the 143 hours. And so you have no awareness of the variability or the transient nature of any of the phenomena in this photograph. It does seem to be a fairly typical area, and it's all very interesting, but you do miss anything that flares or dies or otherwise changes during the stare. So what we've got to do to follow things that change in brightness or move is the equivalent of moving from still photographs to movies. Movies are actually a whole sequence of photographs, usually taken from the same aspect, or at least a chunk of them from the same aspect. And because it's a whole series of exposures, you can see changes in position or changes in brightness. It's only very recently that we have started looking at the universe in this kind of way. until very recently, what we were really concerned to do was to get really deep photographs, and Hubble with its 143 hours of integration was just superb. Thank you very much. There have been a few kinds of astronomers that have been aware of a changing sky. Pulsar astronomers, X-ray and gamma ray astronomers all have been alert to this dimension, and optical astronomers who study novae and supernovae and other variable stars will be aware of it. But quite a lot of those variations are on quite a long time scale. For the pulsars, X-ray and gamma ray astronomy, they're aware of variations on quite short time scales. So supernovae, whoops, sorry, I'm just trying to get rid of a bar, that's it. Supernovae are a well-known kind of transient. You're probably aware that these are massive stars that explode at the end of their lives. It's believed that in quite a lot of the cases, during that explosion, the core gets compressed and becomes a neutron star or a pulsar. And there's been one famous supernova in recent years in the Large Magellanic Cloud. Move on. Right. So this is a photograph of part of the Large Magellanic Cloud. There's a great big cloud of glowing gas and dust here. There are zillions of stars all over the place. And there's a lot of this pink-red stuff. Now, I wonder, have you sussed out what this pink-red stuff is that you find in many, many photographs? The most common chemical element in the universe is hydrogen. And maybe in a physics lab, you've looked at the spectrum from a hydrogen lamp. And it's got a very prominent red line and then some bluey, purpley lines as well. All this pink stuff, red stuff that you see in an astronomical photograph is hydrogen gas glowing like it does in the lamp in your lab. So every time you see pink stuff, red stuff in the universe, you can say, ha, hydrogen. And you'll be right 99% of the time. But what I've really put this slide up for is this. This was previously a very faint star, maybe a bit like that one, really, really faint. And then in one day in February 1987, it suddenly got hugely bright. It was a supernova, a very sudden brightening of a star. What we understand is happening is that it was a massive star. It reached the end of its normal life cycle and exploded. Quite often these explosions leave behind a neutron star or a pulsar. This one, we couldn't find a pulsar, and it wasn't for want of looking. We looked and we tried this and we tried that, and we could see no sign of a pulsar. But just recently, some news has come in from millimeter wave astronomy, from ALMA, the Atacama Large Millimeter Array, which is a very large radio telescope in Chile that does millimeter wave radio astronomy. And they'd been looking at that same patch of sky, and what they see is a lovely ring of stuff, probably stuff heated by the shock front from the exploding star, and in the middle, this. And this bright spot is the exact center where we believe the star that exploded was situated. And the fact that you've got this, what we're seeing is dust, glowing hot, this bit very hot. And it's believed that this is evidence that there is in fact a hot neutron star, maybe not pulsing, in this area. So there are now many telescopes looking for transient or moving things. Moving things would include comets and asteroids, and in particular, killer asteroids, asteroids that might impact the Earth. That's quite a good way of getting money out of bodies like NASA to talk about asteroids hitting the Earth. And this particular telescope here, ATLAS, which is in Hawaii, specifically got money to look out for asteroid impact. It can do other things as well, and does do other things as well. I'll talk a bit more about this telescope, the Palomar Narvsky. It's on Mount Palomar. It's an old dome, and the telescope inside has been refurbished. It's quite a small telescope by today's standards, but it was a great telescope in its prime. And another kind of telescope, another Schmidt telescope, this one owned by the Swedes, Uppsala, but it's situated in Australia. And these are examples of 3 telescopes amongst quite a large number now that are looking out for transient things, things that flare away and die, or things that move in the sky. So typically what happens is you're working in the optical usually. You take a photograph of a patch of sky, or maybe you take several photographs. One particular pattern is to take 4 30-second exposures 10 minutes apart. Then you go away to another patch of sky, lots of other patches of sky, repeat the pattern, come back to this spot 28 days later. The 28 days is so that you get it at the same phase of the moon. And so you'll have the same background light levels, and the photographs will look much the same. And we've got 2 photographs here of the same patch of sky, and lo and behold, something has happened. And in the right-hand photograph, there is an extra object that is not there in the left-hand photograph. Something has flared up, something has brightened, and has been picked up in the second photograph. If you do see a change like this, it's important to announce the discovery quickly so that other people with other telescopes can also go look at it, and between you all get as much data as you can on the thing, whatever it is, while it's bright. Because if it brightens up quickly, it's probably going to fade fairly quickly as well. You don't want to hang around. So back to this telescope on Mount Palomar. Starting a few years ago, they put a new camera on an old 48-inch telescope. It's got a wide field of view. It works in 3 optical bands. And for those who are astronomers, it goes to about 20.5 magnitude. And starting in February 2018, they've used this new camera and telescope to scan the sky. In 3 days, they can scan the sky completely. And when they've done that, they go back and they do it again. And when they've done that, they go back and do it again. And this thing, Zwicky Transient Facility, shortened to ZTF, is finding about 10 explosive transients per year. It's also generating 4 terabytes of data per night. And so the data has to be analyzed by machine, and we're into machine learning, programming the computer to look for things that have changed. Every 3 years, they get 3 petabytes of data. So clearly data streams are important in this game. It's finding each night about 1 million things that seem to have changed. Most of them flaring, a few moved. You see why it has to be done by computer. They're finding new supernovae. They're finding new asteroids. The asteroids do move. They're finding a tidal disruption event every month. I'll say a bit more about what tidal disruption events are. And they're getting a lot of information on supernovae, the exploding stars, and how they interact with their environments. So it's big business, and it's huge data quantities as well. Moving to talk about one particular kind of transient event, which is called microlensing. And I'll explain this mainly with pictures. So in this picture, we have the Earth on the left, and on the right, we have our favorite star that we are aiming to observe. Fortunately or unfortunately, because all the stars in the galaxy move relative to each other, an other star has got between us and our favorite star. And this is not totally bad news, because the gravity of that intervening star will bend the light rays and make that intervening star act a bit like a lens. So you can see here, going from our favorite star, a beam of light, which normally would go away up here, but because of the gravitational attraction of this star, bends down like that. I have to say the angle is exaggerated quite a bit, but the principle is correct. And a ray of light going this way gets bent and comes this way. So you on Earth, for a short while, pick up extra light from this particular star. And your first thought is probably, oh, it's flared. And then maybe you spot this intervening star and you realize, aha, it's a gravitational lens. It's the gravitational effect of that intervening star that's bending more light back to us on Earth. Now, that's interesting, but there can be other nuances as well. So I'll try and explain that with another set of diagrams. So here's your pet star that you're trying to observe. Here's the intervening star, and it's moving relative to your pet star. And so what you, the observer, see is a temporary brightening of your pet star. Now suppose this intervening star has a planet. The planet has much less gravity, but it's still enough to cause a little effect. And what you, the observer, see is the brightening of your pet star. It decays a bit, and then there's a little blip for the planet. And with a bit of practice, you can get to say, ah, not only do I have an intervening star, I have an intervening star with a planet. Sometimes the planet is rather more distant from the intervening star, and we see the brightening due to the star, and then afterwards, separate, the brightening due to the planet, its planet. But what has happened is that some people have found the planetary blip only, and no sign of a star. The planet does not appear to have a parent star. The planet is free floating. Sometimes called an orphan planet, sometimes called a rogue planet. They've found probably about 20 of these now, but they estimate that there are a couple of rogue planets, orphan planets, for every star in the galaxy. That number has yet to be confirmed. That is an estimate, but there might be quite a lot of this kind of brief little transient event happening. So far I've been talking about optical astronomy. I'm now going to move and talk about some other wavelengths. We'll talk about X-rays and gamma rays, and we'll talk a bit about radio. Going first to the far end of the spectrum to gamma rays, transient gamma ray events. And there's a bit of history here and quite an interesting story. It goes back to the 1960s, when the USA signed a nuclear test ban treaty with the Soviet Union. They agreed that there would be no tests of nuclear weapons in the Earth's atmosphere. The USA did not completely trust the USSR and decided it had to do some kind of monitoring to make sure that the USSR was not quietly doing nuclear tests in the Earth's atmosphere. And the best way of picking up an illicit test is to look for the gamma rays that are emitted during the test. So the US put up several very simple gamma ray detectors, gamma ray telescopes. They aim to have 3 satellites at least up at any time. So, and the satellites would be in different positions so that they could get a fix on where the gamma rays were coming from and make sure that, it was from the Soviet Union, from over the Soviet Union. These were called the Vela satellites. And starting in 1967, they found a number of gamma ray bursts. The complication, or the interesting complication, was the gamma ray bursts were not coming up from the Earth's atmosphere anywhere. They were coming down from the sky. So they're not the Soviets illicitly testing nuclear weapons. Something out in the sky is letting off nuclear bombs or is otherwise generating short bursts of gamma rays. The image on this slide is a more recent one, but it gives you a good idea of what a gamma ray burst is like. Along the bottom, we've got seconds, and up the way, we've got the number of gamma rays counted. And there's a quiet ambient background, and then suddenly, wham, there's this great strong burst. And after 20 or 30 seconds, it's gone, and everything's gone back to the nice, quiet, ambient background. Well, the scientists had some trouble getting permission to publish this result because Vela satellites were highly classified. And it wasn't actually until 1973 that they finally got permission to publish that they had detected these gamma ray bursts. And then the big question is, what is it out in space that's producing these bursts? And arguments raged. The arguments became sharper and clearer when a gamma ray satellite called BATSI put out a map showing where 2,700 odd bursts had come from. And this is a map of the sky. It's in galactic coordinates, so the Milky Way would be along here, galactic North Pole up there, galactic South Pole there, and the different colors represent the strength of the gamma ray burst, how many counts there were. Now, if what was producing these gamma ray bursts was something in our galaxy, you would expect to see a concentration along the Milky Way. Sure, you'd get some at high galactic latitudes and low galactic latitudes, but you'd see a concentration. And there is absolutely no concentration there anywhere. That kind of distribution means either the bursts are very, very close and we don't see more distant ones, so of course we don't see any concentration to the Milky Way, or alternatively that they're extremely distant, they're from way beyond the Milky Way, they're nothing to do with the Milky Way, so of course there's no concentration to the Milky Way. These things come in at a rate of about one a day, and it took quite a few years before it was finally agreed what these amazing things, well, not what, where these amazing things were coming from. Before telling you that, I'll point out that during the burst, it's the brightest object in the gamma ray sky by quite a margin. So we really ought to understand these things. Somebody made a histogram of the number of bursts with different durations, and it's a double-peaked histogram with a break at about 2 seconds. And frightfully creatively, they called the ones longer than 2 seconds long duration bursts, and the ones less than 2 seconds short duration bursts. Still doesn't tell us anything about where they're coming from, what's causing them, but there do seem to be two populations. And in fact, we now know there are two totally different phenomena giving gamma ray bursts. So those gamma ray astronomers had discovered two phenomena in one fell swoop. And I will explain briefly at various points what the two phenomena are. The long bursts are the easiest to explain at this stage. And they believe long bursts happen when a high mass star collapses, maybe to make a neutron star, a pulsar, maybe to make a quark star, if quark star exists, maybe to make a black hole. And as part of the collapse, you get a very narrow jet of gamma rays. And if the jet is pointing at your satellite, you pick up a burst. Going back now to the optical astronomy, still sticking with long bursts. They managed to establish that long bursts come from distant galaxies. They had some optical telescopes monitoring the sky when a long duration gamma ray burst was detected. And they were able to get a photograph just about as the burst happened and compare it with an earlier photograph. The two photographs are taken with different telescopes, and there's different signal to noise. You see the background here is really speckledy, whereas here it's fine, lower noise. But you can see a double object, a single object, a triple, a double object, a single object, a triple. This circle marks the error bar or the error circle on the position of the gamma ray source. And at the tip of the arrow, there is a new source in the right-hand image, but nothing in the left-hand image. And it turned out that it was a distant galaxy. So the long bursts come from distant galaxies. And they come at a rate of a few long gamma ray bursts per galaxy per million years. But since we've got millions and millions of galaxies, we get long gamma ray bursts most days, typically. But at least we've established that the long gamma ray bursts are distant, and that's why they don't show a concentration to the Milky Way. Another fairly recently established type of transient event is called a tidal disruption event. Here is a black hole. Here is a star that is going to pass dangerously close to the black hole. All the stars are moving around in galaxies. This could be the center of our galaxy, or it could be one of many other galaxies. So the star is moving, but by the time it's got here, the gravity at this lower point is stronger than the gravity at the upper point, and the star has been pulled into a cigar shape. And then as it goes closer to the black hole, which is somewhere in here, the cigar breaks up into many, many bits. And the bits will fall into the black hole, one after the other, an irregular stream of bits. And as these bits fall in, you get a sequence of optical or gamma ray or X-ray or radio flares from close to the black hole. So you see a whole stream of transient events from near a particular black hole. By now they've seen about 60 of these, or 60 things that might be tidal disruption events. Most galaxies have a black hole at their center, so these things must happen fairly often. I want to spend a bit more time talking about recent developments in radio astronomy where they're finding a new kind of transient. And I have to give you a bit of background physics as well. So we have now done gamma rays, and we're going to radio, and we've done tidal disruption events, which can cover quite a lot in between. But we're now down the left-hand end of the spectrum at radio wavelengths. Reminder of a little bit of physics. You pass a beam of light through a raindrop or a glass prism, and you get a nice spectrum with the colors spread out. There is a similar phenomenon occurs with radio waves. There aren't glass prisms up in space, and they wouldn't do it even if there were, but there are free electrons in space, and free electrons can affect how a radio wave travels, and the effect is different for different frequencies. I don't know if this is going to work. Try an audio clip. It might be worth explaining the diagram above first. We have frequency plotted this way and time horizontally. And there are a couple of fairly broadband bursts of radio energy that show as verticals. And there's this very long spread out one with the high frequencies coming before the low frequencies. it makes a kind of whistling sound. So we'll see if this sound will work. No, it won't. Okay. This is a descending whistle. Now, radio astronomers who study pulsars regularly make plots like this, because if you're interested in pulsars, pulsating radio stars, they're at some distance, and you could easily be confused by a nearby burst of radio waves if you didn't have this kind of plot to separate the nearbys from the distance. So pulsar astronomers regularly I don't know why it decided to go then, but it did. So the pulsar astronomers are studying what are believed to be neutron stars, very small, very dense stars, rich in neutrons. They spin very fast. They sweep a beam of radio waves around the sky, a bit like a lighthouse. And if that beam of radio waves shines on your radio telescope, you see a pulse. And another one period later, and another one period later, and so on. And radio astronomers regularly make these kinds of plots where we have frequency going up the way and time along the way. Frequency up the way, time along the way. And they look for these slightly curved traces to show that the radio signal has come some distance through space. And indeed, the slope of this will give you an estimate of the distance. So this is the intensity that a radio telescope picks up. Here's the pulse from a pulsar. It goes back. And your frequency time plot, your spectrum, shows you this. This is a less clear pulse, but it's there, okay. It's just there's a lot more noise. This is a lot more speckledy, and the curve is a bit less clear, but it's there. And radio astronomers always make these plots so as to be sure they're looking at a pulse from some distance, not local radio interference. So here's another plot made by some pulsar astronomers. This shows the intensity, so it's pretty clean. It's a bit noisy. There's a wonderfully short, sharp, large spike, and then it goes back again. And here is this curve on the frequency time plot. Very nice, until you say, this curve's dropping very slowly. There's a lot of dispersion. There are a lot of electrons along the path from this source. There are more electrons along the path from this source than there are electrons in our galaxy. So this must have come from beyond the galaxy. It must have come from beyond the galaxy. The snag is when you get to the edge of the galaxy and get to, quote, empty space, it's not totally empty, but the electron density is very, very, very low. And to notch up the necessary number of electrons to explain this long, slow dispersion, you have to go one heck of a distance. Really, truly extragalactic. Light years away to another galaxy, probably. It's a highly dispersed signal, implying way, way beyond the galaxy. Well, the astronomers who found this weren't quite sure what to make of it all. Their data looked good, but they thought, we've only got one of these. Nobody's ever going to believe us if we publish it. They finally did publish it, and not many people believed them, true enough. And they kept looking in that direction, and they never saw another pulse like this. And then radio astronomers started finding more and more of these. They're known as fast radio bursts because they're short and fast, and they're radio, and they burst. And mostly they come from where no previous signal has been seen. They are all well and truly beyond the Milky Way, long way extragalactic. There's rarely a repeat, and there's not often a steady signal from there either. And to begin with, they couldn't find any optical or infrared or X-ray. And then they began to be able to locate some of them, and a few have been located, and they're all somewhere in large galaxies, which doesn't actually help us a lot either, because in a large galaxy, there's a hell of a lot of stuff. And dear knows which of the billions of objects in a large galaxy the signal comes from. So these have been an intriguing mystery for quite a while. We've seen over 3,000 of them now. We've got plots here. This is a plot of radio frequency against time. So there's a nice clean burst. This from a different part of the sky. It's there, but it's not very strong. There. It's there. And they all come from way beyond the galaxy at redshifts between 0.5 and 1. A handful have now been seen to repeat. The Australians caused some confusion because in addition to picking up bursts like this, they were picking up other bursts that look a bit different. Not hugely different, but a bit different. And they were happening all over the place. All times, well, not all times a day, from all over the galaxy, apparently. And a grad student made a plot of when these funny bursts occurred, plotted against local time. Not something you normally do in astrophysics, but this grad student did. And there was a large peak in the frequency of these bursts between 12 noon and 1 p.m. local time. Now, this telescope at Parkes in Australia is away out in the boondocks. And about half a mile away, there is a house where astronomers can stay with a little kitchen, with a microwave oven. The radio astronomers had tested that microwave oven. They knew it did not leak microwaves, but they did begin to get a bit suspicious. And they set up a test. One scientist in the residence kitchen with his mobile phone standing near the microwave, and the other scientist in the control room at the telescope with his mobile phone. You don't normally have mobile phones at radio telescopes, but this was necessary. And the scientist in the residence would set the microwave oven going and then stop it by opening the door. And the guy at the telescope said, "Yep." And they repeated the experiment, "Yeah." And they repeated the experiment, "Yes." If you stop a microwave oven by opening the door, it doesn't switch off immediately. There is a short burst of microwaves. This short burst of microwaves will probably hit you in the chest. Frequent exposure is probably not a good idea. I'd recommend stopping a microwave using the stop button, not by opening the door. So the Australians managed to eliminate their funny, curious bursts, and we were left with ones like everybody else was seeing. We still weren't too sure what they were. There's a new radio telescope in Canada. It's in the Rockies, in amongst the mountains. It's in a valley, and the mountains provide quite good shielding from stray resolution. This is a close-up of part of it. It's a mirror, metal mirror for radio waves. It's actually a cylindrical mirror, and so it's got a line focus. And there are 4 troughs like that across here. So it's got quite a large collecting area, and it's picking up lots and lots of these fast radio bursts, over 3,000 now, as well as studying the hydrogen in the universe, which is what it was meant to do. It's still not very good at positioning the bursts, but it is notching up the number of bursts very well. The Australians have managed to position some of the bursts, a few of them, and they are somewhere in the outskirts of massive galaxies, as I've already mentioned. And yeah, there's quite a lot to the outskirts of massive galaxies. So we're not a lot the wiser, but we're making some progress. So just a minute or two to talk about what's going to happen in the near future. There is a big telescope building in Chile, an optical telescope, 8.4 meter diameter. This is a model of it. There's a human being to give you scale. There's another one. It's known as the Vera C. Rubin Observatory, and it's going to particularly look for transient events, things that change their brightness on quite short timescales. Its camera is about the size of a small car, and it will have 3 billion pixels. The numbers vary, but it's going to produce somewhere between 1 million and 10 million alerts per night as it scans the sky. An alert is, hey, something's flared, or hey, something's moved. It's going to catalogue 6 million solar system bodies. I didn't realize there were 6 million bodies in our solar system, but it's going to find them, and 37 billion stars and galaxies. And it says it's going to release the data on transients within 1 minute of readout. The snag is, with this quantity of data, there is no way people can analyze it. It's got to be done with computers. There's a new radio telescope being built. It's called the Square Kilometre Array. That's going to be the area of, that's the collecting area of the telescope, the area of the dishes. Some of it's going in Australia, some of it's going in South Africa. This particular image is of the first bit in Australia. There's a similar first bit in South Africa. It's known as the Meerkat telescope. And the Meerkat telescope is picking up a number of these fast radio bursts. What they've rather cleverly done is, in amongst the Meerkat radio telescopes, they've put a small optical observatory. And the optical telescope is slaved to the radio telescope. It points in the same direction. It observes the same bit of sky at the same time. So if the radio telescopes pick up a burst, you dump the optical data and see if anything is visible in the optical that's changed or brightened. They're calling it Meerlicht. Meer means more in Dutch. And of course, South Africa has Afrikaans, which is derived from Dutch. The final topic, which I'll be very quick about, is gravitational radiation. If you take a pair of stars which orbit each other, as they orbit, they disturb space-time. They cause ripples in space-time, and these ripples fan out. A bit as in this animation, although the waves are never as large and clear and distinct as they are in this animation. They travel out at the speed of light. So that was a pair of stars orbiting each other. Because the pair of stars are emitting this radiation, the radiation carries away energy, the pair of stars loses energy, and that causes the orbit to shrink. And with a shrinking orbit, the period gets shorter and they go round faster and faster, which means there's actually more of this gravitational radiation, so they shrink more and go faster, which causes more gravitational radiation, which causes them, etc., etc. They ultimately merge. The waveform, if you could pick up these gravitational waves, looks a bit like in this image. To begin with, there's the very quiet rotation of the two stars, but gradually they're getting closer, the period's getting shorter, the amplitude's getting bigger, and finally they crash together and merge, and you get at the end quite a strong gravitational wave signal. In 2016, they managed to make the first detection of a pair of objects merging. It turned out to be a pair of black holes, each about 30 solar masses. We did not know that black holes of such a mass existed, but they obviously do, because the gravitational wave detector called LIGO has found quite a lot of them now. And there were actually two detectors, and trace the signal from one is in the salmon color and is in blue from the other. And to begin with, they're all out of sync, but here they're beginning to get in sync. And the amplitude's growing and the period's getting shorter and the amplitude's growing, and wham, they merge and it's all over. Many of the gravitational wave things detected have been black hole mergers, but they have had now two a pair of neutron stars merging 2 times. The first one was quite exciting because LIGO detected the merger of the two things. The gamma ray astronomers detected a short burst of gamma rays. And optical astronomers using the gamma ray position managed to see the aftermath. There was something to see following this merger of the two neutron stars. And what we think is happening for the gamma rays is the two stars are orbiting each other. They are in-spiraling. They ultimately merge. There'll be a narrow burst of gamma rays coming out along the rotation axis. There may be gamma rays at other angles. There's certainly light as well. And so the short gamma ray bursts seem to be associated with gravitational waves from the merger of neutron stars. So a lot has happened in the last few years. Transient astronomy is now becoming a really big part of astronomy. We have by no means bottomed it out. I think there's going to be a lot more interesting transient events coming along. So watch this space, as they say. I think there's a lot more to come. Thank you very much for your interest and your attention. And back to you, Hannah.
Great, thank you so much, Jocelyn. If you'd like to stop sharing, we can take some questions. Thank you so much for that very wide range of topics that you discussed, and very insightful in each of them as well. So we've got a number of questions, so I'll jump right in. So we've got one question, which is, do the after effects of supernovae count as one of the possibilities for fast radio bursts?
We thought it might do, because supernovae give the pulsars and the pulsars give repeated bursts. But it's not obvious that supernovae would give a single burst. Not clear how that would happen, to be honest. There may be something we're not understanding properly, but at the moment, that's not featured very high amongst the possibilities.
Okay. All right, thank you. Someone's asked, can you recommend any books to read in terms of astrophysics detection and transients?
I'm afraid it's too new a field for books.
Okay.
I think you do better Googling transient radio sources or fast radio bursts, something like that. And you'll find both technical articles and less technical articles.
Okay. What is the status of detection of flares from F and G types of stars? Is there an expected number of detections from the Rubin telescope for these events?
I think the Rubin telescope will undoubtedly. I'm afraid I don't know how many one expects from F and G stars.
Okay, great, thank you. So slightly more general question. So you've covered a range of topics. What do you believe, and you touched on this, what do you believe are the next most important discoveries to be made in this field?
The field has given us so many surprising results. It's actually quite hard to predict with any confidence. I'm sure we'll get better at understanding the tidal disruption events when things fall into black holes. As we get more fast radio bursts, we'll get better at saying something about the host galaxies that they come from. Well, I can see a number of things notching up quite a bit with the Rubin telescope, assuming they get the data analysis working okay.
Yeah, there's great need for machine learning in this as well. So.
Yep, indeed, absolutely. But how do you program machines to look for things you don't know exist?
Yeah, and there's that. During your pulsar discovery, did you have any doubts that it was anything noteworthy, or did you feel you were onto something pretty immediately?
I was fairly convinced this was something most unusual. Mm-hmm. The thesis advisor was cautious, and we had to check out everything, that it wasn't a flaw with the telescope, that it wasn't interference, that it wasn't this, that it wasn't that. Mm-hmm. I found a second source, and then a third and a fourth, all within a period of a couple of months, 3 months. And when you've got more than one, you feel a lot better. It's right. When you've got one funny thing that you're in a very uncomfortable position.
Yeah, but then when it starts to repeat itself, then you know that you, yeah. Okay, just check any more questions. Yeah, we've got a few coming in. Lots of comments thanking you. Viewers. So something that we ask all of our speakers is do you have any general advice that you can offer students or researchers that are just starting off in terms of how to shape their research focus, and just general advice?
Well, your thesis advisor will probably have in mind some area, some topic, some branch of the field. It's worth, a good way to start is worth delving quite well into that. But equally, it's a good idea to attend lots of talks and hear what else is going on. It may give you ideas, may help you think out of the box, which is sometimes quite important as well.
And sort of after your PhD, when you're moving into shaping your own sort of field, any sort of tips or advice on how to go about that?
Well, I had quite a difficult time because I got married as I finished the PhD. And at that time, married women didn't work. Married women were housewives, full stop.
Right.
Wanted to work. And so I was scrabbling around for jobs. I went from radio astronomy to gamma ray astronomy. Mm-hmm. And then when my husband moved job to another part of the world, I got a job in X-ray astronomy. And then when my husband moved job, I got to infrared and millimeter wave astronomy. Right. That is not a normal career. Okay. It's huge fun, but it was not a normal career.
Right. Okay.
It is, the two-body problem is quite an issue.
Right, yeah.
For children as well, and you need to find child-minding nurseries, that kind of thing. It gets pretty complicated. And as I think we've seen during the COVID lockdown, it more often falls on the woman than on the man to solve some of these issues.
Yeah.
Still falls on the woman.
Yeah, absolutely great. Yeah, again, lots of comments coming in, thanking you. So one question, do you think it's more difficult to identify objects today as opposed to when you found the pulsar due to the increase in electronic devices here on Earth and in space?
Yes, interference of all sorts is a problem. There's a lot more radio emission around these days here on Earth. With those satellites, communication satellites going up, the Starlink satellites, that could be an enormous problem for optical astronomers. There's some talk about painting them a dark color, which will be better. Mm-hmm. Even so, a whole load of communication satellites is bad news for many people. Good news for others, but bad news for many astronomers. Really, as the world gets more crowded, there's more interference.
Yeah, okay, makes sense. I mean, that's a problem we'll have to sort of learn to tackle in the future. Sure, yeah. Right. Well, thank you very much for your time and for sharing your insights as well, and some of your more personal insights as well. It's been a pleasure to have you. So very, very grateful for your presentation, and got lots of comments coming in thanking you very much for answering questions and for your presentation.
You're very welcome.
Thank you very much.
For my records, could you give me an estimate of what the attendance has been?
Yes, absolutely. Sure, I will do. I'll give you all the information.
Thank you very much. Thank you.
Thank you very much, Jocelyn. Take care.
And yourself. Keep well too.
Bye.
Bye-bye.